So here's another way of looking, and I don't think I showed you this plot yet, of looking at the 9 groups. We know that there are 9 groups in the data. The question is does the data, are the 9 groups different from each other? Well, principal components is one way to make a plot. So if I put this in my paper and I color this according to which one they're in, I'll show you how to do that in JUMP in a little bit, then it provides information for my paper. The points are clustering together. Another way to look at the data that's really simple, and I've told you multiple times, you have to try PCA on your data, because it might, if this plot comes out, life is good for you. This is telling you a lot of information about your data. Like group 9 is wildly different than the other groups. And then I can go to the PCB people and show them this dendrogram, which is sort of useful. Or I can show them this PCA plot and they go, oh, that's cool. And they tell me about how group 9 is different from all the other groups, because they know that stuff, and I don't, as the statistician. Group 2 and 3 are sort of overlapped. That may be logical. Group 1 and Group 4 are completely overlapped, but the groups are pretty tightly clustered. I mean, even 5 and 6 are pretty far apart from each other, even though they're right next to each other. So this is a very useful plot. Now, adding a third dimension, I wonder if I actually have this data. Adding a third dimension would be super cool, because a third dimension might allow me to distinguish between these 2 overlapping groups. Remember, I'm only using 2 principal components. The principal components are linear combinations of the variables that I have. So how is the cluster analysis different? It's grouping the points together. These are clearly points. Each one of these, so that's a point in my data, in my multivariate data, but it's being summarized as a combination of all the variables. Whereas if I'm doing cluster analysis, I'm not doing any combination of the variables. I'm just seeing which points are close together. Well, which ones are the most tightly clustered in this picture? Maybe group 8? Group 8's like pretty much right on top of each other. So it's probably true, since they group together in the principal components, that they're pretty close together. By the way, not necessarily. Probably the group 8 ones are those down there. These guys right here, that are all close together. They're probably not these guys, which have some that are pretty close together, but then these guys don't get joined in until up here. I don't know, that's why you need color to help understand what's going on. But the dendrogram does not use linear combinations of the data. It uses the actual data. There's only distance involved between the multivariate points. So it's different. It's also not intended. Neither of the cluster analysis is not intended for discrimination. Principal components is not intended for classification. It turns out that both are helpful in visualizing how classification might be done. If I'm doing classification using cluster analysis, and I have an unknown, I can find out the unknown. What do I do? I guess I figure out where I could throw the unknown into here and see where it clusters, see where it's close to. So I guess that would work. but it's not the intended purpose for cluster analysis. Oh yeah, the real part. So the tree says something, the dendrogram, the principal component says something. How are you going to argue that the clusters that you find are real? Well, principal components helps a lot. If principal components this clearly says that there are clusters in the data, even though it's using linear combinations. So it's validation of some type. A different software approach is finding groups in the data as well. There's a number of slides coming up that talk about how many clusters do you have. So is this 9 clusters or 13 clusters or 5 clusters, or how do you decide? Very little is known based on hierarchical clustering, how to make this decision. The methods described here are I've never seen in a paper. And I've seen a lot of cluster analyses. And nobody's using these approaches. Instead, they look at the dendrogram and they have a feeling. Sorry, but even though the cluster analysis is a very computer sciencey approach, no statistics involved, they still make the decision based on their mood when they're writing the paper. Fortunately, in a lot of the cases, it's really obvious that and they use color to help make the decisions. And I'll show you how this has been modernized since we made these slides probably 10 years ago. So there are 2 measures that can come out of the software. One called a pseudo F and a t-squared statistics. And there's this cubic clustering criteria. And I guess I have seen that one used. Basically, you make something that looks a little bit like a scree plot. And this one is the cubic clustering criteria. And evidently, if you plot this, it suggests this is the number of clusters here, and the cubic clustering criteria is over there, and this says you have between 6 and 10 clusters. We happen to know that there are probably, what is the, go back to this picture. How many clusters are in this data? 1, 2, 3, 4, 5. Maybe those grouped together 6, 7 maybe from the PCA. So maybe there's 7 clusters in the data. But maybe with more dimensions I can tell the difference between these groups. So there might be 9 because there are 9 classes. You kind of suspect the right answer is 9. So the fact that the cubic clustering criteria said maybe 6 to 10 is probably pretty accurate. This is something called pseudo t-squared. Never seen it in a paper. Doesn't mean that people don't use it. And evidently where there are who knows? What's the actual criteria? Suggests 5 clusters because it leveled off maybe there? I don't know. Like I said, never seen it. Doesn't mean that you won't use it or see it in a paper. It means I haven't seen it. This is something called a pseudo F value. The decision is somehow does something I guess the book says something about it on page 292. I don't know. Finite amount of time in life. If you zoom in on that plot, if you zoom in down here, and software is good at this these days, you get that 6 to 12 maybe, because it's leveled off. The statistic is not increasing as you increase the number of clusters. And so basically these are, if the clusters are tightly compacted, then making more clusters, and if we split we take group 8 and we split it in half, who cares? We're not gaining much in grouping the data points. So that's basically what's happening in that picture there. There's some old links that I wonder if they actually work. The cluster expert, I wonder what that one is. Oh, this is from the textbook. So the links probably still work. Unconvinced. What you should be convinced is you're going to see cluster analyses, and people are going to ask you to do cluster analyses, and it makes sense. Makes perfect sense to do a cluster analysis. You just have to remember what you're doing. And if you're a statistician, then doing a cluster analysis is